Okay, greetings aspiring scientists. Welcome to my video today on metallic character in periodicity and acid deposition. So let's get right into it and go to my slides. So we are now in 3.1.4 in the classification of matter in the structure section of IB Chemistry SL. Metallic character and periodicity. So in my previous videos, I've talked a lot about the trends on the periodic table. I've talked a little bit about metallic character. So let's review metal properties. Metals usually have certain characteristics. They're good electrical conductors. Pure metals are a lattice of protons and a sea of electrons which can move fairly freely, and electricity is the movement of charged particles. So electrons being able to move freely provides an opportunity for a charge to flow, and that is electricity, conductivity. Malleable. For similar reasons, metals can be reshaped with an appropriate force. There's no sort of localized bonds that say that, either the electrons or even the protons in the lattice need to be in certain positions. They're sort of free to slide around and change their shape when forces are applied. Ductile. For similar reasons, metals can be pulled into thin wire shapes. Lustrous. When absorbing photons, electrons are free to move and oscillate, which allows a perfectly opposite wave to emit. We're not really going to get into the details of that. That's more of a physics thing, I think. But just be aware, many metals do reflect light very well, like a mirror. So we're now going to consider some reactions that metals have, and consider the fact that reactivity and reactions are a part of metallic character. So the more that these type of reactions happen, the more metallic character you can say. And when I say the more it happens, what does that mean? It means how spontaneous it is, how exothermic it is, how quickly and vigorous it is. So one of these standard reactions that you must remember, you should look at this a few times and remember it and practice writing the general equation so that you can write it for any alkali metal. So this goes right along with combustion and neutralization, things that you really need to remember for IB exams. So alkali metal with water. Here's a general example. 2 metal atoms in the solid phase plus 2 H2O, water molecules in liquid, goes to H2 gas, hydrogen gas, plus 2M plus, aqueous, dissolved in water, plus 2 OH minus, aqueous. Those are dissolved hydroxide ions, OH minus. Okay, and very often, instead of M plus and OH minus, you might see this written as MOH, because basically these will stick together when the water is evaporated and it is treated as a hydroxide salt. So something like NaOH will form when the water is removed. So you might see NaOH as something in the products instead. So metals with lower ionization energy react more vigorously. And similar reactions can occur with alkaline earth metals in group 2 as well. This general equation I'm showing here is just for group 1, the alkali metals, but there will be similar reactions for alkaline earth metals I'll show on following slides. So this reaction releases hydrogen gas, but don't go out and do this yourself thinking you're going to get hydrogen gas, because it's fairly dangerous and flammable if it builds up. So make sure you're in a controlled environment with someone who knows what they're doing. And it also leaves a basic solution with metal ions dissolved in it. We can see there's 2 M plus and 2 OH minus. So 2 OH minus, the more OH minus you add, the higher your pH is going to get, the more basic solution you're making. All right. So that's, the metallist of metals is the alkali metals. Let's move over to the other side of the periodic table with low, very, very low metallic character. These would be the halides. So an important reaction that you have to know is halide with halogen. What does that mean? Well, the halogens are group 17. Fluorine, chlorine, bromine, iodine, and so on. Halides are the anion versions of those. So we're actually reacting like two halogens together, but one is sort of the pure element and the other is the anion version. So halogens are highly electronegative. They can oxidize many different compounds because a lot of energy will be released when they gain an electron, so that tends to happen. They will even oxidize other halides, which are halogen anions, if the halide is less electronegative, right? So you can imagine these things come together, maybe you have a collision, but the electron will go to the more electronegative element. So for example here, F2 plus 2Cl minus goes to 2F minus plus Cl2. You got to think about this carefully. So if you consider their electronegativities, F is the highest, 4.0. Chlorine is high, but still less. It's like 3.2 or something. So when these collide and come near each other, F will take electrons from Cl minus. You have to consider that Cl minus has its own extra electron, right? Cl minus, if you draw its Lewis structure in the top right corner here, this has gained an extra electron that it owns. Okay, it owns that extra electron and it's happy to have it, very stable. Whereas in F2, it still has a filled octet, but only through sharing. So there's a pair of electrons here in the middle that completes both of their octets, but this is shared and not owned by each one. So it's not actually very stable. So shared instead of owned in F2 means that when F2 collides with Cl minus, it will reverse these roles. It will force Cl2 to share with another neighbor Cl, and it will take that electron that Cl minus had for itself, because F is more electronegative, and overall the system will be more stable this way, where F has its own electrons, and Cl2 is forced to share with its neighbor. Cl2 doesn't really want to share either. It's not that stable, but it's more stable than F2. So this is the way it works, and you can make this whole table I've written on the right side, halogen halide reaction table. So F minus, when mixed with anything, is no reaction, any of these halides and halogens anyway, because it's the most electronegative, 4.0 on the scale. So once it gets an electron, it's going to take some miracle or some crazy amount of energy to remove it. Just mixing it with other halides and halogens won't do anything. Okay, but if you mix F2 on the top with chloride anion on the left, there is a reaction. F2 takes the electrons, chloride loses them, we form F minus and Cl2. But any other mixture with chloride doesn't actually work, right? Chloride with chlorine or bromine or iodine in the second row, there's no other reactions because chlorine is the second most electronegative halogen. So once it gets the electron, it's not going to give it to any others except for fluorine, F2. Okay. So then you can see this pattern follows. Bromide will react and give its electron to fluorine, and it will react and give its electron to chlorine. But with bromine or iodine, no reaction. With iodide, this will give its electron to any other halogen, gives it to F2, to Cl2, to Br2, but mixed with iodine, I2 itself, no reaction. So very important to familiarize yourself with this type of reaction. Halogens exchanging electrons to form pure elements versus anions. Very common paper 1 question, I would say. Okay, let's move on. So, as you can imagine, since halogens are very electronegative, and they'll be very stable if they gain an electron, and then alkali metals have very low ionization energy, doesn't take much energy to remove their electron, then of course, halogens can oxidize alkali metals by taking their electron. So here's the general equation. 2m solid plus x2, that's the halogen gas, goes to 2mx, a new salt, metal halogen salt. Oops, just let me go back. So I'm trying to think of some examples, maybe like lithium metal with fluorine, F2, we'll make lithium fluoride salt. Pretty simple. So that brings us to the end of this section. It's not very long. It's just introducing you to some of the most common reactions for the most metallic elements, alkali metals, and halogens. So number 1, write the reaction between potassium and water. Potassium is K. So we have some solid K plus H2O, liquid. All right, this is going to go to something. And then what have we learned? And what have we learned? This is going to go to H2 gas, hydrogen gas, plus metal ion K+, dissolved in water, AQ, plus hydroxide ions, OH minus AQ. Now we've got to balance this. So I think we'll have 2K, make 2K plus, 2H2O, 2OH minus. So we should have 2K on each side, yes. 4 hydrogen on each side, 2 and 2, yes. And 2 oxygen on each side, 2 and 2, yes. Okay, so that's what that looks like. 2, list the alkali metals in terms of their reactivity with water from least to most reactive. So you can just consider periodic trends and go in one direction along the periodic table. So the least reactive alkali metal will be the one with the highest ionization energy. It's lithium first, then sodium Na, then potassium K, then rubidium Rb, then cesium, and then francium. So francium should be the most reactive with water. Francium is very rare, so I don't think people usually would do or show that reaction, but it's more of a theory thing. Okay, then 3, identify the most reactive pair. It's important to understand what this means. So the most reactive pair will come from the combination of the highest electronegativity or the greatest electron affinity, the greatest need for an electron, mixed with the lowest ionization energy. Okay, so one of these nonmetals, electronegative things, is going to come pick up an electron from a metal, but to remove an electron from the metal still takes a little bit of energy. The ionization energy is a positive amount of energy, right? So it's going to take a little bit. So the lower that little bit is, the greater the net energy released can be. So let's consider this. 3A, F2 plus KCl or F2 plus Ki. So this looks like, halogen gas, pure element with a salt. But what you really need to think of is one of the previous slides I show you. This will be F2. Really, it's reacting with either Cl minus AQ or I minus. And I guess we don't have any evidence that this is aqueous in water, but I think we assume it. I don't think this reaction will go quickly at all if you just mix gas with solid salt. So, what did we say? We said F2 will basically take an electron from the other halides. It's more electronegative, so both of these reactions will go, but which one will be the most reactive? It's going to be the one that has the least electronegative anion. So in this case, I-, or in the salt form, Ki. Iodine doesn't really hold its electron nearly as tightly or as closely as chlorine. So the reaction that we would expect to be more reactive, more vigorous, F2 plus Ki, just because I has lower electronegativity than Cl. Okay, 3b, Ba barium plus I2 iodine, or Ba plus Cl2. So we want to go a similar approach here. This one, though, is a metal with a nonmetal halogen, pure element. So both of these reactions, I think, would also go. The halogen will take the electron. But the most reactive, again, it's going to be a combination of the lowest electronegativity on the metal, so it's going to lose its electron easily, combined with the greatest electronegativity, or the greatest electron affinity, on the nonmetal, on the halogen. So in this case, chlorine is more electronegative. It wants that electron from barium much more than iodine. So most reactive there. C, Li plus I2, very similar here, just instead of alkaline earth metal, we have alkali metal. So in this case, again, look at electronegativity. In this case, fluorine has the greater one. So that's the biggest difference between the ionization energy of lithium and the electronegativity of F. I2 doesn't want electrons nearly as badly as F2. Okay, 3D then. Moving on, K, potassium plus Cl2, or Li plus Cl2. Now we're changing the metal part. Cl2 is standard, so I think both of these reactions would go. Cl2 wants that electron, but for the metals here, going down the periodic table decreases the ionization energy. That's what we want for a more vigorous reactive reaction. So in this case, potassium will lose its electron much more easily, much faster, and more exothermically. Okay, so those should be the answers. Let's move on. All right, 3.1.5, metal and nonmetal oxides. So we're now going to look at when metals and nonmetals bind with oxygen. It's a very common case here on planet Earth. There's so much oxygen that many things end up being oxidized to their most stable states. So metal and nonmetal oxides. Most elemental metals can be oxidized by oxygen. Oxygen will come take their electrons, and this produces an oxide with a number of oxygens depending on the number of electrons needed to complete the octets. So oxides must also react with water. Some produce basic or alkali solutions, and some produce acidic solutions. And the trend sort of follows metallic character. More metallic things, more metallic character elements form more basic oxides. Less metallic then form more acidic oxides. So let's look at the metal oxides for alkali metals. So we know metal oxides react with water, and they will split it to make metal hydroxide salts. These remain dissolved in solution and create a basic solution. So here's the general formula first. M2O, metal 2 of that with one oxygen. So these would be alkali metals, something like sodium oxide, Na2O, or lithium oxide, Li2O. Plus water goes to 2 metal hydroxide, 2 MOH. And then a real example here, Na2O plus H2O goes to NaOH. So we're going to have metal ions along with hydroxide ions making a basic solution. Okay, metal oxides with alkaline earth metals. So now looking at group 2, also highly metallic, but slightly different equations here. MO solid, where M is an alkaline earth metal, plus H2O liquid goes to MOH2. So now just the numbers and the number of OH groups is a little bit different because these alkaline earth metals will lose 2 electrons to reach their most recent stable noble gas configuration. So then a real example, magnesium oxide, MgO plus H2O goes to MgOH2. But very similar to with alkali metals. So alkaline earth metals form similarly basic solutions. Okay, so let's think about this. Metal oxides with non-metals then. So going to the other side of the periodic table. Non-metal oxides react with water and combine with it to make acidic oxides, which are capable of releasing H+ ions into solution. So we have not studied acids and bases really yet, but I've mentioned a few times that things that release H+ or hydrogen ions more are considered more acidic. So that comes into play here. These dissolve into solution and create acidic solution. And I had a couple examples there. So non-metal oxide with carbon, CO2, and water that can make carbonic acid, a weak acid. Sulfur dioxide, non-metal sulfur with oxygen plus water goes to sulfurous acid. Sulfur trioxide with water, sulfuric acid. Phosphorus oxide with water, phosphoric acid. So all of these will make acidic solutions. This brings us to in the middle when there's a shift between metallic and non-metallic character, things like metalloids. Some compounds in the middle of the periodic table, for example metalloids, can produce basic or acidic solution depending on what they react with. The most common example, especially in IB here and on IB exams, is aluminum oxide, Al2O3. This can neutralize acids or bases depending on what is in the solution that it might be placed in. Now, aluminum is actually considered a metal usually, but it's really near that metalloid staircase, so it's near the shifting position of metals and nonmetals. So again, there are many definitions of acids and bases, but generally acids release H+ into solution or remove OH- from solution. Both of these will make the solution more acidic. On the other hand, bases generally release OH- into solution or they remove H+ from solution. Again, either of these will make the solution more basic. So let's consider aluminum oxide, Al2O3, placed in 2 different solutions. If it's placed in an acidic solution with something like hydrochloric acid, HCl, it will exchange its oxygens with chlorines to make AlCO3, and those oxygens will mix with the H's from HCl to make H2O. So we've really removed H+ from solution there, because HCl, if you've studied acids and bases, you'll know it 100% dissociates into H+ and Cl-. So even though we write HCl, AQ there, really they separate 100%. That's going to release a lot of H+. That's a lot of acidic solution. But in this reaction here with Al2O3, the H+ gets kind of scooped up by the oxygens in Al2O3 and makes water. So it is a kind of neutralization. So in the presence of hydrochloric acid, excuse me, aluminum oxide accepts protons, H+, and reacts to form aluminum chloride and water. So it is behaving as a base when near a strong acid. But if you put it in a basic solution, maybe NaOH solution, Al2O3 plus 2 NaOH plus 3 H2O, makes this kind of strange complex with aluminum. Aluminum will have 4 hydroxide groups, OH4, and overall that will be negatively charged, and it will kind of be balanced by the sodium Na plus ions in solution. But once those hydroxides are bonded to that metal center, Al, they're no longer in free solution. They're no longer really contributing to basic solution conditions. So in the presence of sodium hydroxide, aluminum oxide absorbs hydroxides and reacts to form sodium aluminate, sodium tetrahydroxoaluminate. So here it behaves as an acid. Okay, it's not releasing H+, but it is removing OH- by complexing with it. So IB loves to use this example. Make sure you know it pretty well. Okay, moving on. So we have a little comparison table here. We have our oxides on the top, starting with the most metallic and then moving less metallic as we go to the right. And let's consider the solution when these are mixed with water. Na2O, definitely basic. MgO, definitely basic. Those will make OH- in solution. Al2O3, amphoteric, we should say, because it depends on what's nearby, what it will do. Could be acidic or basic. SiO2, though, acidic. P4O10, that should be. Okay, P4O10, I showed on a previous slide, that will be acidic. SO3 and SO2, also acidic. So it is kind of another periodic trend that we can learn as we go through a period left to right. We get more acidic solutions when metal or nonmetal oxides are dissolved in water. So the last kind of thing in this section is about acid deposition. This is an important sort of environmental concern. There's a lot of chemistry involved, and IB loves to test people about this. So again, very important to know. So acid deposition is the process of acid-forming compounds depositing on Earth's surface. So whereas the acidic compounds might be locked underground or locked somewhere in the atmosphere, when they fall down through rain, usually, and deposit on the surface, this is what we call acid deposition. Acid rain is the most common form of acid deposition. Acidification, which is basically just something being hit by acid rain and having a low pH solution on it. This will cause damage to structures, causes many dangerous chemicals to become more soluble in water. And when toxic chemicals dissolve in water, they can flow and travel easily. They become much more mobile than if they were like a powder or a rock or something. And they can easily flow and seep and leach into unwanted areas. So let's see some examples. Plants will absorb more dangerous chemicals through their roots when acid rain is nearby. Acid rain will... The main thing it does is, oxidize metals so they become ions, or it can attach to organics that normally would not be soluble in water and make them extra polarized and extra soluble. And then the plants suck up these solutions in their roots and gain a lot of toxic things in their branches and leaves and all the structures, and usually end up dying. Fish absorb more dangerous metals. So once these metal ions that have been oxidized get into lakes or rivers or ponds or whatever, they're now more mobile, flowing around, dissolved in the water, and the fish will either eat things or breathe it through their gills and absorb dangerous metals and other compounds. Also, just in terms of buildings and structures, limestone and other acid-sensitive buildings, there's quite a few, but limestone is clearly one of the weakest. These corrode and degrade when in contact with acid rain. And I want to dive just a little deeper into sort of the fish and the food chain idea. So industrial pollution, this used to be much more of a problem, but I'm sure it still is now. They'll dump their waste products into lakes or rivers or whatever, or oceans. And although they might be just metal pieces to start with, or like pure things like iron or mercury or lead or whatever, once acids are nearby, they tend to oxidize these metals and make them more mobile and easily absorbed by organic material that's living there. So fish, or the food that fish eat, absorb these, and once larger fish eat those smaller food sources, these things kind of just pile up. They don't go anywhere. They don't tend to exit organisms, so they build up inside the bodies of these larger fish. And this has created many problems over recent years since the Industrial Revolution, I'd say. Especially in Japan, where I live, one of the worst cases, I think it was called Minamata disease with mercury. So yeah, these are big problems. Some of the biggest problem culprits are shown here on this slide. Hg mercury, Pb lead, Cd cadmium, and As arsenic. And this is why people generally recommend that you don't eat a ton of fish, even though fish is really healthy. Especially larger sort of predatory fish have high buildup of these metal ions, which mainly come from acidified metals. So why would rain be acidic? Let's consider this. So even without, pollution or the Industrial Revolution or volcanic activity, rainwater is acidic. And the reason is because there's so much CO2, carbon dioxide, in the atmosphere. CO2 is naturally present, and there's really nothing we're going to do about that anytime soon. And CO2 is generally good for plants and stuff to make food, so we wouldn't probably want to remove it all anyway. So with CO2 in the atmosphere, this is produced by respiration of animals, decomposition, volcanic activity, and combustion. It exists as a gas and becomes dissolved when it contacts liquid water. So CO2 actually dissolves in water. You should know this if you drink soft drinks, right? Those have high amounts, but even small amounts will always be dissolving. Then, the formation of carbonic acid. Dissolved CO2 can react with water to form carbonic acid. That's H2CO3. That is one of the acids that I recommend you just memorize the formula, carbonic acid. This reaction is relatively slow, and the equilibrium favors the left. Only about 0.3% of dissolved CO2 is converted at any time. So we are making this carbonic acid, but not much of it really exists at any one time. Like 99.7% of the CO2 in water will exist as separate entities. But some will be H2CO3. Then we get dissociation of protons from this weak acid. So carbonic acid is a weak diprotic acid. In the first dissociation step, it donates a proton H+ to water, forming the bicarbonate ion, HCO3-, 1-. So this is the dominant dissociation, and it's primarily responsible for rainwater's slight acidity. And then we have a Ka here. If you studied HL, acids and bases, you'll know what this means. But generally, if this number is bigger, it means more protons are released. And if it's smaller, it means less of the time they are released. So 10 to the -7 is a very small number. That's not very many protons being released. Now, H2CO3 is diprotic. That means that it can release another proton to go to CO3 2-. But this one is even less likely. Ka 10 to the -11. That's like even 1,000 times smaller than the first one. So although this is possible, it's almost insignificant, I think. We can see where this puts rainwater, normal rain on a pH scale. If 7 is our neutral in the middle, we're at 5.6 for normal rain, slightly acidic, but it won't really have the effects that I've discussed with like fish and plants and building damage. It would be very slow. So what is the problem then? The problem is when rain contains strong acids. If you studied acids and bases, you'll know that strong acids release all of their protons. So primarily sulfuric acid, H2SO4, and HNO3, nitric acid, are the biggest problems here on Earth for acid rain. They are strong acids. Both can be formed by natural events like volcanoes, or by human activities like burning fossil fuels in factories or vehicles. Well, let's consider it. Starting with nitric acid, strong acid rain. So the problem is nitrogen monoxide, NO. Okay, now this is quite a rare form of nitrogen. Most of the nitrogen in the atmosphere is N2. It's just very stable, two nitrogens bonded together. But every once in a while, in extreme temperatures, you'll have very fast collisions between molecules. And if you have oxygen and nitrogen, you'll break them apart and reform them as chemically bonded NO, nitrogen monoxide, or nitric oxide. It's a colorless toxic gas. Now, it won't really be made in toxic quantities usually, unless you like take a pipe from your exhaust in your car and put it in your window. But most of the time, if it's just dispersed into the atmosphere, then it's not really a concern. But if you're just releasing it millions of cars day after day, it does become a problem overall in the atmosphere. So next, atmospheric oxidation. NO oxidizes to nitrogen dioxide, NO2. Just coming into contact with other O2 molecules. O2 is a medium strength oxidizer. So once emitted into the atmosphere, NO rapidly reacts with oxygen in the air. This produces nitrogen dioxide, NO2. This is reddish, brown, terrible smelling gas, and it often creates like reddish orange smog when it's present in polluted areas. And this step is essential because NO2 is the reactive species that ultimately leads to nitric acid. So if NO just stayed the way it was, it might not go to nitric acid, but because it is further oxidized to oxygen here, it will eventually end up as nitric acid. All right. Now the next step is fairly complicated. NO2 reacts with hydroxyl. I think in most IB textbooks, this will just be shown as reacting with water, H2O. But in more detail, it's actually water breaks apart into OH dot, which is OH radical that has an unpaired electron once UV light separates it. So that OH minus attacks NO2 in a fast gas phase reaction. This is the dominant daytime route when there's sunlight to break apart water molecules into OH dot. And this will cause HNO3 gas. Okay, and then once that's been made, it can just, come into contact with water droplets in clouds, for example. Nitric acid has extremely high affinity for water. It is scavenged almost completely from the gas phase into cloud droplets and falling rain. Once it's dissolved, it is a strong acid and dissociates nearly completely. Alright, so then once we have HNO3 AQ, it's basically all over. All of those H's will remove themselves. HNO3 goes to H plus NO3 minus, the nitrate. So unlike carbonic acid, nitric acid is a strong acid. It dissociates essentially completely in water. Every mole of HNO3 releases 1 mole of H plus. Same thing as saying every atom releases 1 ion of H plus. Dramatically lowering the pH of rainwater to 4.2 to 4.4 in heavily polluted regions compared to 5.6 for clean rain. So you can kind of see that on the pH scale underneath. We had clean rain with carbonic acid at 5.6, but now we'd be going down to 4.2. Remember that the pH scale is logarithmic, so going from 5 to 4 would be 10 times more H plus. And we're actually going, almost 1.5 pH units difference, 1.5 lower. So that could be more like 50 times more H plus in the HNO3 acid rain. Okay, sulfuric acid. This is the other big troublemaker. It also makes strong acid rain. So what's the idea here? So sulfur is present in impurity in fossil fuels like coal and oil and in volcanic rock. When these fuels are burned or when volcanoes erupt and have sort of combustion effects, sulfur is oxidized to sulfur dioxide, SO2. This is a colorless and pungent gas, principal precursor to acid rain, and it is emitted in hundreds of millions of tons globally every year, some from volcanoes, some from factories, some from vehicles. So the key equation, S solid plus O2 goes to SO2. So next, I think several things can happen, but SO2 can oxidize to sulfur trioxide. Now in most textbooks, it will just show SO2 reacting with oxygen, O2, but the process turns out, I think, is more complicated. It will react with hydroxyl radicals as well, make some weird radical species in the middle, and eventually SO2 will be converted to SO3. I'm not really going to go into detail on that. because it's more advanced than we need to know. Now, the problem is once you've made SO3, it's highly reactive. Sulfur trioxide in the gas phase reacts vigorously with water vapor or liquid water droplets to produce sulfuric acid. So it's just SO3 plus H2O. There's lots of H2O in the clouds. That makes H2SO4 immediately. Now, another issue is sometimes SO2 dissolves in water immediately before it is oxidized to SO3. This is the second sort of major route. The second major route occurs inside cloud droplets and on wet aerosol surfaces. SO2 dissolves in liquid water to form sulfuric acid. So this time, SO2 plus H2O goes to H2SO3. Slightly different, the less oxidized sulfur version of a sulfur acid. But the thing is, this is not really that stable. It won't stay that way for very long if there's oxidizers nearby, and there often is. Even something like H2O2, hydrogen peroxide, or ozone. And this will just oxidize it further by adding one more oxygen on that sulfur, and you end up in the same place at H2SO4. So whichever of these pathways ends up happening, it's not really that important. The important thing is that they all kind of lead to H2SO4 as one of the more stable ending points. Okay, so once you've got H2SO4, again, it's all over for acid rain. This H2SO4 will essentially release H plus 100% to make H plus and HSO4 minus. But sulfuric acid is a strong diprotic acid. The first dissociation is complete and instantaneous in dilute aqueous solutions. Every molecule donates its first proton to water. This will form the bisulfate ion, that's HSO4 minus and H plus. So this step makes a lot of protons in the water. pKa equals -3. Again, if you studied HL acids and bases, you'll know what that means, but basically it means 100% or nearly 100% dissociation of H plus from H2SO4. Now this can even go further to dissociate the second proton to make SO4 2 minus. Now that pKa is 1.99, so it's not 100%, but it's like perhaps similar amounts to the carbonic acid before, or even stronger than that. So it definitely does have an effect, and it has potential to add extra H plus to solution. And you can see on the scale, pH scale then, it goes down to 2.4 for H2SO4 acid rain, way below clean rain and even farther below nitric acid. And you might even have nitric and sulfuric in the same rain depending on your pollution sources nearby. So that's a lot to remember. You probably won't remember it, but in summary, I think this is what you should remember, okay? NO can be created, nitric oxide can be created by high heat combustion, basically anywhere, because there's N2 and O2 in the atmosphere everywhere. So anywhere where there's high temperature, this can be made. And it will react with O2 and H2O, water and oxygen in the atmosphere and in the environment, to make HNO3, a strong acid. On the other hand, sulfur exists as impurities in fossil fuels. When they are combusted, they'll make SO2. SO2 can react to make SO3 or H2SO3, but in the end, those will react with water to make H2SO4. So the key to remember here is that you have your problem oxides, nonmetal oxides with nitrogen and sulfur, mixed with reactive atmosphere species oxygen and water vapor or water liquid. And on the right side of these equations will be the problem strong acids, HNO3 and H2SO4. So try to remember that. Try to be able to explain a little bit about what happens. Generally, it is oxidation and reaction with water. So finally here, there's a little cycle you could imagine where volcanoes and power stations release sulfur from the ground, oxidize it into SO2. SO2 can react to make SO3 or react with water. It will make acid rain. This acidifies lakes, fish die. It acidifies the area around trees, trees die. It erodes buildings, it corrodes metals. We didn't talk about that too much, but that can also definitely happen. Things that have metal structures like bridges can corrode. And, eventually the sulfates or the salts will potentially go back in the ground, maybe be reduced by some chemical processes under high heat and pressure, and be released by volcanoes and burning of fossil fuels later on. But that cycle will take a long time, to get it back in the ground and reduced again. So once we're oxidizing it, we're sort of accelerating this process of corrosion and acidification. All right, so that's all I have for today. Kind of random jump into acids and bases, a jump ahead, but I think these topics are really important for IB exams. So hope you learned something. Good luck and see you next time. Bye-bye.